Alrighty, everybody. Let's take a look at this atwood machine that we were looking at today. That is a little bit of a challenge for us, but that's all right. Um, so let's start with a basic drawing of what we were working with. We had an object on an inclined plane. We had a cart attached to a string, pulley, second mass, come down here. It was a little copper mass. And based on what I saw from folks, um, let's see, this one was about 0.271 kilograms. This one was 0.514 kilograms. Now, depending on what class you were in, some things went smoother than others. Um, but the best way we looked, or the smoothest lesson that we had about this happened in the 8th hour class. So I'm going to approach it the same way we approached it in the 8th hour class to try to make it a little easier on everyone. In 8th hour, what we did was we started with the inclined plane. Okay, so we're going to do the same thing there. All right, so start with a free body diagram. This object was, as I'm sure you're aware, was accelerating up the hill. It was getting faster and faster as it went up the hill. When we take a look at our forces involved here, most of these are pretty straightforward. We recognize them. And then this one, some folks forgot about, but didn't take us long to figure out we needed friction as well. Okay, so we've got tension going up, the normal force with the surface, Fg, because we always do, we're never leaving the earth, and then of course friction going down the plane because it's going to resist that motion. The next thing that we like to do, as I'm sure you're aware, is we're going to break up the gravity into, well, you know what, a lot of you guys are calling them y and x. Not a problem, as long as you know what they stand for. Fg, sorry, not sine of theta, cosine of theta. And this one is Fg sine of theta. Okay, so we've got those. What we are able to do, because we know the mass, is we're able to calculate all of these. The other thing that we did before we left school yesterday is we came up with a coefficient of friction for the object as it slid up the inclined plane. And that mu, I believe we found, was somewhere around 0.22, maybe 0.121, 23, 24, depended on your rounding. But it was somewhere in the 0.2 range. Okay, so at this point in the proceedings, what you would do is go and figure out everything you can figure out based on the numbers that we have. So you know Fg, here, let's change colors again. All right, so Fg, that's going to be mg, right? And then, so, you know, we're looking at what, 0.5, where did I write it? 0.514. That doesn't look like a 5, does it? 0.514 kilograms times 9.81 meters per second squared. Right, we're going to do that. Then we can do mg sine of theta, mg cosine of theta. All right, now assuming assuming you can do math, I would assume you can do those. But just to be fair, I culled some answers from my group, so they may be slightly rounded a little bit differently, but I just grabbed that paper as I walked out the door to get here. So my cosine was 4.94. This allows me then to figure out friction. So, you know, 0.22, 4.94. That's going to give me my friction. And my friction worked out to be about 1.24 newtons. Okay, we figured out quite a bit here. All right, so let's face it, what do we know? We know this one. We know this one. We know this one because this is also our normal, right? These are the two that are equal and opposite of each other, so those two are the same. The only one we don't know is tension, right? That's going to be the wild one. That's going to be the wild card that we don't know. So we are at a point in the proceedings where we can write a balanced force or a net force equation. Right? We know that net force is equal to mass times acceleration. It's also equal to the Grady equation of bigger minus smaller. The question then really goes to what the heck are we talking about, bigger and smaller? So let's start with the left side of the equation, 0.514a. I don't know A, and I'm also, you notice I don't know tension. But when we look at our inclined plane, Let's just double check. What is trying to pull us up the hill? Tension is trying to pull us up the hill. What is trying to pull us exactly opposite of tension? And this is what I see a lot of mistakes on when we do inclined planes. You have to look, if this is going in this direction, you want what's absolutely opposite. This one and this one. They are both going in the exact opposite direction. So when we say bigger minus smaller, the bigger one is the tension, because we know we've seen it go up the hill. So tension's got to be bigger. The smaller ones, it's a combination of friction and what you guys are calling X going down the hill. The good news is, let's face it, we know what some of these are. Here's my force of friction, right? X, that's our sine theta piece. We know that one too. You got to be careful about distributing the negative, but in the end, we pretty much have everything we need on this equation. All right, so when I do the work, when I get the final equation, I get 0.514a equals t minus 2.37. Oops, let's make sure we can see that. I must be at the bottom here. All right, let's try that one more time. I'll write it a little bit higher. There we go. 2.37. Now that may not seem satisfying because I still don't know A and I still don't know T, but there's the second piece we haven't even considered yet. Okay, so this is a really important equation. This is our first equation. Our second equation is about the hanging mass. All right, so this was the one that was going down toward the floor, right? And it had a mass of 0.271 kilograms. All right, so when I ask about what we've got going on, we've got tension here, we've got Fg going down, a different Fg. But of course, we can find it pretty fast, right? So that is not an issue. What is an issue is, well, or at least what I saw was a little bit of, well, what exactly is happening here? Which of these is going to be bigger? Which of these is going to be bigger? And this is where you have to really consider which way is it going? What did you see? You saw it getting faster going this way. That tells you that gravity is bigger. And I did actually have a very intelligent response to this, but you said gravity doesn't change unless your mass changes. Absolutely true, but just because gravity doesn't change doesn't mean it's not bigger than the tension. It can be, absolutely. So net force, I'm just going to call this one 2 because, you know, actually I could put it right in here, is again going to be equal to the bigger force minus the smaller force. The bigger force is the one going down. Tension, the one going up, is our smaller force. All right, so when we consider Fg, if you multiply that by 9.81, you get 2.66 for Fg. You still don't know the tension. And then there's your second equation. And again, maybe that's not very satisfying because you don't have a final answer. But we are just a little bit of algebra away to finding what the acceleration of the system is, or what the tension, or both, depending on what you need to do. Right here, we're looking at a system of equations. So I'm going to take a minute and I'm going to put down the other equation. I'm going to show you two ways to solve this. All right, so my other equation, 0.514a equals t minus 2.37. All right, and I'm going to come back to this side of the board in just a moment. But what I'm going to do first is the most common way that I see general physics students solve this question. And nothing wrong with that. Let me show you what I tend to see. This is what I tend to see. The 0.514a equals t minus 2.37. I'm going to get t by itself because then I can do some substituting, right? Now I can't really do a whole lot with these values. I can't exactly really combine them, but I can do that. And what this allows me to do is to take this and put it here. I can put it at that spot. So if I do that, then I can move things around. No, I got it. Okay, that doesn't look like a 1. Let's try that again. I'm going to make sure I distribute the negative sign. Okay, I want the a's all by themselves, so I'm going to add 0.514a over here. And then I'm going to take these two and I'm going to add them together on the right-hand side. Okay, so what I end up with is 0.785a equals 0.29, and then I can solve for a. And my a works out to be about 3.369 meters per second squared. Okay, so there we go. That's the acceleration of the system. Now let me show you how we do this in AP Physics, because I know you're desperately interested in knowing that, but I kind of like doing this because it saves me a couple of steps. So what we do in AP Physics, we take the equations and we line them up like this, and then we add them together, which is another way of doing substitution. And what I like about that is it kind of puts the a's on one side automatically, and it takes care of the t's on the other side. I mean, if you didn't notice, it's a positive t, that's negative. So they cancel, and then I can add these two together, and oh, lo and behold, I get exactly the same thing that I got before, without all the extra moving around. And the truth is, I really have no cares about which way you think is easier for you, as long as you could do that sort of algebra. All right, now, the big questions. The big pressing questions. Let's give myself a little bit of space here. Hopefully, well, you know, you can always rewind, right? If you were looking to write that down. Here's our first big question. Is this on the test? Because dang, this is hard. No, it's not. Then why did we spend this time doing it? That just seems like a waste. Well, actually, I disagree with you. All right, we may not be doing Atwood machines as, you know, like what I'm going to actually be testing you on. Let's face it, we've got 5 more days till our group test. This is like really the peak of where we've been. But it's been really good practice for this baby. And this we've seen quite a bit. And to be blunt, you all have struggled with it. Not every single person, but as a collective, this is where we are weakest, is with an inclined plane. So it's another example of an inclined plane and how to resolve them and so forth. The second thing I want to point out is that specifically with the inclined plane, what I notice as the problem is that you're always setting these two equal. Or maybe this one and the friction equals to the tension. You're always assuming it's balanced. And you know what? Sometimes it is balanced, but sometimes it's not. Sometimes it really depends on what's happening. Is the object rolling down the hill? Then it's not balanced. And, you know, bigger minus smaller applies. So it's a good practice. We need that every once in a while. So it was what I had originally hoped to do. My big ambitious plan was to have you go out even further and then apply our velocity stuff to this so you could figure out using a VT graph just how much time it takes for the object to hit the ground, how much it took for the copper piece to fall to the ground. But we ran out of time, and that's okay. Not a big deal. We can definitely consider that at another date. But the acceleration from this system would allow us then to draw a VT graph and come up with that. But, you know, as often happens, we just kind of ran out of time. So my hope is that now you can add this to your workbook so you have an Atwood machine to look back on. You can use it as reference and consider it practice for inclined planes, which is kind of the key. And what happens when we have more than one body? We make a system of equations and we solve them. All righty, that is us for today. Have a happy rest of your Friday afternoon and a great weekend.